Okay, today we're going to do our first inference process. It's going to be a one sample Z interval for true proportion. So what I want to do is I want to kind of walk you through the process of how you do something like this. So we're going to be presented a problem that's going to kind of look like this. What do you want to be when you grow up? According to a nationwide survey of a random sample of 1,000 kids under the age of 12, some kids want to be a ninja, a dragon keeper, a dancing unicorn, and even an octopus. 55 of the 1,000 kids want to be a doctor. We would like to use this study to find a 98% confidence interval for the true proportion. So here's the deal. In this process, we're given a lot of information. We're given here the sample size. So in this case, we know that the sample size of this is 1,000. We're also given the confidence level. So we know that we're going to be doing a confidence level of 98%. And we're also given some numbers here. We know that 55 out of 1,000 want to be a doctor. So what we know is that P hat is 55 out of 1,000. And when you do that 55 out of 1,000, you're going to get 0.055. So it's kind of important to make sure you kind of have that P hat. So this is the information we're given. Now here's the deal. When we do a problem like this, there's a lot of information that it's expected that's not explicitly stated. So what you need to do is I want you to use this acronym, and the acronym, oddly enough, is called PANIC, P-A-N-I-C. So we're going to use this acronym PANIC, P-A-N-I-C. And each one of the letters stands for something that we're talking about in the problem. So the P stands for stating the parameter in context. So what we're going to do is we're going to state our parameter in context. So I'm writing down the explanation, but then I'm going to write down in a different color what I would actually want to see from you. So in this case, what we're trying to figure out is the true proportion of kids who want to be a doctor. Since it's a parameter, it's the P without the hat. P equals the true proportion of kids who want to be a doctor. So you need to express this up front, state your parameter in context. The next part is A, and A stands for validate our assumptions. And this is what we did in chapter 7, that random independent normal. I need to do that every single time. So I need to go ahead and I need to validate random. And in this case, it says a random sample. It states random. So what that means is that this is an unbiased estimator. That's what it means. It means that P hat is an unbiased estimator. It means it's a good measure of center. That's what it's going to mean. It's going to mean that random has everything to do with kind of figuring out the center of the distribution. So what I now know is I know that P hat is 0.055 from up top here. My next check is independent. And right now, again, I'm going to stick with the independent check. That's 10n. So we're going to take 10 times our sample size, and we're going to compare that to our population. We're going to see if that's a true statement. Later on, we're going to change it when it's an experiment, but right now we're still going to stick with the 10n. So we're going to do 10 times 1,000 is 10,000. And we're comparing that to our population. It's a nationwide survey of kids under the age of 12. I think it's safe to assume more than 10,000 kids 12 and under nationwide. And because I did that, what I'm allowed to do is I'm allowed to actually figure out the standard deviation. And in this case, what the standard deviation is going to be is it's going to be something slightly different. We're not going to use P like we did in the previous chapter, chapter 7, because here's the deal. We don't know the real answer. All we know is what we figured out here in the survey. All we know is that P hat. So what we're going to do is we're going to use that P hat as our measure of standard deviation. So instead of P, we're replacing it with P hat. So this standard error is what it's going to be called. It's referred to as a standard error. Is going to be this. We're allowed to use this. I plugged in the number for P hat in both places. I plugged in the 1,000. This guy is called standard error. has a different name. It's my standard error of my statistic. P hat being my statistic. This guy's my statistic. And here's the deal. You don't ever really need to simplify it, to be completely honest with you. It's not necessary to. You're allowed to just leave it like that. The calculator is going to do the work for us. Our last check is it's the normal check, or we're going to start referring to it as a large enough check or a large size check. Since we're dealing with proportions, we want 10 successes and we want 10 failures. So if you remember before, that was that NP greater than or equal to 10 and 1 minus P greater than or equal to 10. But again, in this case, we don't know P, so we're just going to use our sample as our best guess. In this case, it's really going to be nice because if you think about it, we had 55 successes, 55 kids said they wanted to be doctors, so we met that criteria. And what we could find out is that if we did 1,000 minus 55, that would equal 945. We have 945 failures. So that tells me that the shape of this distribution is approximately normal. And here's the thing that's new here is now, since we can do that, we're going to be able to use, and on your formula sheet, you have this table B. I know it says T distribution. Don't worry about it right now that it says T. We can actually use the infinity row down here. And if you look way down at the bottom, there's a bunch of confidence levels. And these are called critical values. It's the number of standard deviations I'm going to give either direction. So in this case, since I'm talking 98% confidence, I'm going to look at the infinity row. If I drag my finger across the infinity row, 2.326. That's my critical value. So again, what this allows me to calculate is it allows me to calculate my critical value. And it's based on my confidence level. The critical value at 98% was that Z star equaled 2.326. So now what I have is I have all the components I need to construct my confidence interval. So A has got a lot of writing, I'm telling you, it always does. Then N, what I'm going to do is I'm going to name my interval. And its confidence level. So in this case, what I'm going to do is I am going to construct a one sample Z interval for true P, true proportion at 98% confidence. So I'm telling the reader what I'm doing. So I said, here's the parameter I'm looking for. I've validated that I've met all the criteria to do what I need to do. Now I'm going to tell you what I'm going to do. My next step is I'm going to compute my interval. And the way I compute my interval is what I'm going to do is I have this formula. And the formula is this, P hat plus or minus Z star P hat 1 minus P hat over N. Now, what I want to show you is this is not exactly on the formula sheet. Now, a lot of times I say a lot of the stuff's on the formula sheet. This one's not directly, but I want to show you that on page 1 of the formula sheet near the bottom, there's this idea of confidence interval. And it gives you this formula, statistic plus or minus critical value times standard error statistic. So this right here is going to be the P hat I figured out. This is going to be the Z star that I figured out. This is going to be the P hat 1 minus P hat over N that I figured out. Now it tells you how to, like, the components to make it up. If you flip over to page 2 on the back, here's your standard error of your statistics. So this is your one sample. And the thing you're going to remember is since we're not using P, we're doing P hat here. So the pieces are kind of there, but not directly. So what I need you to do is, you don't necessarily need to write it down with the letters, but I do need you to write it down with the formula. So we know that P hat is 0.055 plus minus. We know that our critical value is 2.326. And we know that our standard error up top is going to be 0.055, 1 minus 0.055 over 1,000. And now what's really nice is you don't need to simplify that by hand. You're going to pick up your calculator. And the way you're going to do that is you're going to go to stat. You're going to arrow over to test. And what I want you to do is I want you to arrow down, and we're going to use a lot of these. You're going to use letter A, which is 1 prop z int, and hit enter. So I'm going to write that down. You're going to use A, 1 prop z int. It stands for 1 proportion z interval. And then what you're going to do is fill in the numbers that it says. X is your number of successes, 55. N is your sample size, 1,000. C level, confidence level, 0.98. And we hit enter. And what it's going to do is it's going to give us a range of values. So what it's going to do is it's going to say that this expression right here simplifies to this range, 0.03823, comma 0.0717. Copy it down exactly as it appears there. Don't round anything. Don't truncate anything. Write it down exactly as it appears there. That's my confidence interval. That's my 98% confidence interval. And the last thing I'm going to do is C. I'm going to state my conclusion in context. And that's that sentence I wanted you to memorize. We are 98% confident, because that's what it said, 98%. The interval from 0.03823 to 0.07177 captures the true proportion of kids who want to be a doctor. So let me kind of pull up. So from a high level, you can kind of take a look and see what we got here. That one question ends up with, you've got to go up higher than that. That one question ends up with all of that work. That's what a confidence interval is. What we've done is we've developed for ourselves a range of potential values of what we think the real answer would be if we actually went out and talked to the entire population of kids 12 and under. So in this case, I would expect it to be somewhere between 3.8 and 7.2%. And then there's usually follow-up questions that come out of this, like, would you be surprised if the real answer was 10%? Well, yeah, I would, because 10% is not in my range. We're also going to talk about what happens when I play with this number here, 98%. If I want to be more confident, let's say I wanted to be 99% confident, my interval would get wider. So it would be maybe more than 3.8 to 7.2. It might be like 3.7 to 7.3. If I was less confident, I'd want my interval to go down. If I played with the sample size goes up, standard deviation goes down. So what that means is this number here would get smaller, which means my interval will get narrower. So if I talk to more people, this range would be narrower. If I talk to less people, the range would be wider. So that's what a confidence interval is. Folks, it's writing. So I just need you to be prepared for it. And that's the expectation in a question like that. When I look at a question like that, it doesn't explicitly tell me to do that, but I do have to do that. So please ask me questions if you have it, and please practice when I give you the practices.